Okay, recording is started. Can you guys see this?
Yes.
Yes.
Okay, full run through, Jake, when you're ready.
Okay. I'd like to welcome everyone and thank you for joining us online in these weird circumstances, but thank you for joining us. I'm Jacob Eisenhart, the team lead for the open source ultra low cost sensor array for a tunnel oven team. We'd like to give a special shout out and thank you to our advisors, Dr. Ruber and Dr. Rumbaugh, for helping us throughout this last year. Next slide, please. So our team, as you can see on the left side, going left to right, is Alex Ferlan, who is in charge of our programming, Tony LaRosa, who is in charge of prototype design and production, Michael Kishlar, who worked on the budget and testing, Michael Moldovan, who assisted with software and with testing, and then myself, the team lead. So our team last semester actually was in Nantes, France for the entire semester, working with a school called ONIRIS, which is a Grande Ecole, equivalent to a graduate school in the United States. And they are a food science and agricultural engineering school. So we were partnered with their food science department, developing a sensor array for them to calibrate tunnel ovens, and then also to ensure the proper cooking temperature of like bakery and food products. So in France, this industry is very important in their economy and in their culture. Everything has to be baked daily. So freshness is of the utmost importance to them. Anything that's not sold at the end of the day has to be thrown out, unlike here in the United States. So freshness is the utmost importance to them, so they need to make sure that their ovens are working and calibrated and their food products are cooked properly. Next slide, please. So on the left here is that sensor unit I was telling you about. We call it an LCA. So the DAC, the DAQ, data acquisition unit, is what we're working on developing, and that takes in data from the outside sensors, and that DAC unit then is able to store that data and able to export it then to a computer. We have to have thermal protection since these are going through tunnel ovens. We have to be able to protect that data acquisition unit as the temperatures in these ovens can range anywhere between 200 to 250 degrees Celsius. And on the right there, you can see that is a commercial product that's out on the market that is currently being used to calibrate tunnel ovens, as you can see here, right in the middle of their production. So that's something that we're basically trying to replicate, with the utmost importance being with the height. As you can see, even though it is wide, it is very thin. So that's something that we have to take into consideration. Next slide, please. So this is actually not the first year of this project. It started back in 2016 with the initial creation of the concept. And then the year after that, the design and fabricated the high temperature test bed that we used in France. And then last year, they worked on the further development of that DAC unit using different Arduinos and incorporating more thermocouples and temperature sensors. And we're also able to implement simple on-off control. And our goal was to create a family of LCA prototypes using past year's research, and then also reduce the footprint. As I said, height is of the most importance, so we want to make sure we can reduce that as much as possible. Next slide, please. So our team set off with 4 objectives, and they were to develop a 6-to-8 thermocouple microcontroller-based sensor array, to test that sensor array, to assess its behavior in the oven to make sure that those circuitry components could survive, and then third, to shrink that sensor array to meet the dimensional specifications. As I said, height is of the utmost importance to us, so we want to make sure we minimize that. And lastly, we want to integrate that with a computer, so we're able to export that data and analyze it and manipulate it. Next slide, please. So in this presentation, Tony will be covering the proof of concept in prototypes 1 and 2, and then Alex Ferlan will be talking about software. Michael Moldovan and Michael Kishlar will then be talking about testing. Then Michael Moldovan will be talking about the PC software that he developed. Michael Kishlar will then be talking about the budget for our project, as cost is very important to us. And then finally, Tony will be talking about the final prototype design and giving us a conclusion. So now I'll turn it over to Tony to talk about that proof of concept.
So the proof of concept was really us doing initial prototyping, nothing necessarily official, nothing more than an Arduino with the breadboard, as you can see on the left here side, with like loose wire circuitry to make sure we knew how these amplifiers and thermocouples in the Arduino worked and how we would eventually want to use them in later prototypes. And so one thing that we knew was important was size requirements. So that we were using Arduinos, looking into smaller Arduinos, an efficient layout because breadboards are very large and not necessarily compact, easy to modify. So we wanted all of our prototypes to be able to be modified so that we can adapt them for specific needs, or if something's not working, we can change it out. And then external control so that you don't have to get into the circuitry to control the actual device. Multiple thermocouples because that's a requirement from our the scientists at ONIRIS, and industry standards most have multiple thermocouples, and then very cost efficient. And that comes from what you can see on the left, which is a device from industry, the Digitron ThermoPro 2. It is a DAC unit for a tunnel oven with a steel and ceramic casing, thermal barrier, and it has 16 thermocouples. It can be controlled externally. This one is completely self-enclosed, and it measures to be 6 centimeters thickness with the thermal barrier. So we were shooting to make something similar to that, but the whole proof of concept was to start implementing features incrementally to make sure one thing works before the next. And so from this, we built our prototype 1, which has external switches and LEDs for controlling it, so you don't have to get into it to control. An internal power supply. It has its own enclosure, so it's not this loose prototype on a table. It has a robust wiring, a tight wire, since we're using breadboarding, and so we want the wires to be able to stay put and not to move around. An internal memory of the Arduino was used in this, since we picked the Arduino Mega, and that has the computing power and the memory that we wanted. And completely self-contained, and for the price of $127, almost 130, which is a lot less than the 10 to 35,000 that you can spend on the DAC unit shown in the previous slide. So to dig a little bit deeper in this, it is 14 centimeters across, which is our base we're using when we go into future prototypes. Like I said, it has multiple switches and LEDs, which you can see closer there. It has a battery compartment, tight wire circuitry. You see in the top right, those are the amplifiers on a breadboard with the thermocouples leading out of them. And the breadboard is oriented horizontally, so it takes up a decent amount of space, but isn't necessarily too tall. And yet again, we use the Arduino Mega. We do have to open the top to connect to it, to the PC, to be able to access its memory. So from that, it was a little large, it was a little clunky, a lot of free space on the inside. And so one thing we wanted to do with the second prototype is make a smaller one, build a smaller footprint, more efficient software, more efficient controls, and add more features and more thermocouple connections to it. So one thing the other one, prototype 1, didn't have was proper barrel jack connections for thermocouples. We landed on barrel jacks since they were readily available and easy to manufacture and easy to manipulate to be ports for the amplifiers. And so as you can see there, it is very compact. We used a smaller Arduino, and we used the Arduino Micro with an external SD card, since the working memory of the Micro was not enough. We wanted to make sure we had enough memory for whatever the customer wanted to throw, so we used the external memory card reader and external memory card. We simplified to one switch. And as we go on the next slide, you'll be able to get a better view. So we have a single control switch and 2 indicator LEDs on it to make it a lot simpler. It's only 10 centimeters wide instead of 14. The battery compartment, can't really change that space layout. We'll use a different compartment that didn't take up as much space. We used perf board instead of breadboard, and so that allowed us to orient some things vertically to get that footprint a lot down. And then you can see the barrel jack connections on the left. And then also to connect to the computer, instead of having to open it up, we implemented a port on the side for micro USB serial communications between the computer and the DAC unit. And on the right, you can just see a closer angle of the vertical orientation, the control switch, and that micro SD card reader. So now Alex will take us into software.
All right, so for our software, we had to have certain development goals to bring it in line with our goals for the project as a whole. Those goals that we decided upon were that we were going to use up to 8 thermocouples. The software had to support for that. It had to take accurate readings within more or less 5 degrees centigrade. It had to store at least 30 minutes worth of data without overwriting or otherwise corrupting the data. It had to be simple to use, so you don't have to be an electrical engineer like us in order to use the software, or use our system rather. The data had to be easily transferable to a PC so that you could conduct your analysis on it and actually use it. And lastly, we had to use open source libraries so that we wouldn't have to use or deal with licensing or anything like that. Next slide, please. So this year, we decided to start from scratch with the software. The reason for this being that last year's code that we had inherited had some major problems. They had a lot of very nice features. However, the core data collection and storage system didn't work as intended. So this time around, we made sure that we would start simple and we would get the core functionality down before we started adding features. So that's what we did for our first prototype. We kept things simple. We used only 2 thermocouples on this prototype, as Tony mentioned. For our code, we used a delay function that would busy wait in order to time our readings. Obviously, this isn't ideal because the system is going to be busy waiting. You can't do anything while it's waiting. We used internal flash storage for storing this data. This internal flash storage was very easy to use, but it was also volatile. So if the system turned off, you would lose all your data. Lastly, we transferred data through blind serial data dump, meaning the Arduino did not check and see if there's anything listening in to receive the data. It would just start printing to the serial console. So if you didn't have your computer connected and you didn't have a serial console open to the right port, you would lose all your data. All these things are inconvenient, but they did make programming the Arduino very simple, and they made it easy to figure out where things went wrong if they did go wrong. Next slide, please. For our second prototype, we wanted to improve our functionality. At this point, we had ironed out all the kinks in our original code, and now we wanted to make it easier to use. This time around, we also have it can also use up to 4 thermocouples. This time we use timer interrupts instead of the delay busy waiting function. This time we can actually do other things in between readings. We use a micro SD card for storage instead of the Arduino internal memory. In addition to being larger, it is non-volatile, so you no longer have the risk of losing your data from a power cycle. And lastly, our serial communications now use a text-based UI. This is actually how we control the second prototype. So instead of having a switch on the outside for dumping data and then no signals coming from the computer, now everything comes from the computer. When you connect your computer and you open up your serial terminal, you can send commands to tell the prototype to take samples to transfer the data from the SD card to the computer. And you can even adjust the sample rate, all without having to change the software loaded onto the Arduino. Next slide, please. This is a block diagram of our second prototype. As you can see here, our prototype will read in temperature from the environment using its 4 thermocouples. Those thermocouples create a voltage differential, which then our thermocouple amplifiers interpret and then communicate with the Arduino Micro in terms of degrees centigrade. This data is then stored in the micro SD card, and the indicator LED, as indicated above, lights up to show that we are communicating with the SD card. Whenever you connect the computer to the Arduino, you can send control signals such as the aforementioned starting, stopping samples, or dumping data from the Arduino to the computer. So that will load data from the SD card and send it from the micro to the computer. Next slide, please. All right, here is a block diagram of the code for our second prototype. As you can see, there are 2 main blocks here. One is the data collection block, and the other is the user interface. The core of this program is a small loop above the user interface block. Here, the Arduino will continually loop and wait to see if it receives a serial message. If it does, it will then break over to the user interface block, at which point it will parse the message and determine what actions to take, be that clearing the data on the SD card, dumping the data, meaning printing it through the serial console to the PC, set, changing the sample period, and start and stop, doing what it says on the tin. It'll start and stop taking samples. We can also query the Arduino for a list of valid commands. And of course, if you send something that's nonsensical, it will tell you that. At which point it will return to the wait loop to see if it receives a serial message. Now, if the timer interrupts that we have tied to the data collection, tied to rather, fires during this time, it will first check to see if the Arduino is recording. We have a recording variable that the start and stop functions modify. And if it is recording, it will then store this data on the SD card. It does this by creating a string, adding a timestamp, which is the uptime of the Arduino minus the uptime at which you last called the start command. Then it adds the temperature readings from all 4 thermocouples to that string, and then it prints the string to a text file on the SD card. Again, you can access this SD card by taking off the lid and pulling it out, but ideally, you can print that right through the console using our new UI. So that about covers the software for the Arduino. Now I'll pass it along to Michael Kishlar, who will talk about our testing processes.
All right. So for our testing, we have our individual thermocouples, and we wanted to make sure right off the bat that we had accurate readings from these thermocouples. In order to accomplish this, we researched what the industry was doing, and they were using ice bath tests so that you can ensure, because you're expected to see a 0 degrees centigrade from the thermocouples. And then we could ensure from our test that we actually had valid thermocouples because we were seeing this temperature range from the experiment. Going forward in our next graph, we actually, since we had a different lab environment than that seen in the States, we used we had junior mechanical engineers with us. So we had them research for future groups for this experiment, various materials for the thermal barrier to see which had the best insulating properties with the high temperatures they were seeing. And they found out that the aerogel was the most effective at keeping the temperatures at bay. Now for the next graph, we performed experiments inside of the oven. So we actually have our thermal barrier and the DAC sensor unit that Jake talked about inside of this oven in the thermal barrier. The blue line shows the temperature of the oven. It's a bang-bang controller, so the temperature goes up and down, fluctuating around the temperature we'd see in industry. And then we have the red line, which is the actual temperature of our unit. This was used without phase change material, which is essentially just an ice pack to keep the temperatures low and also not having us to purchase expensive equipment to accomplish this. But we can see that without the phase change material, before even 10 minutes, you're already exceeding the required temperature we want to see in our container. So for our next experiment in the next graph, we utilize the phase change material. Here we can see again in the blue, we have the temperature of the oven fluctuating up and down, but this time our circuitry is actually staying cool. The temperature, as you see, actually goes down once we put it in the oven in the gray area, signifying that we did have a working experiment that showed that we could keep the temperatures down in the high temperature environments. This next graph is the final test we did in France, our proof of concept of prototype 1. Here we have, again, our units inside the oven, but this time we are making sure that the thermocouples are reading the correct temperatures. So we also had vernier lab data, taking the internal temperatures of the oven as well to ensure that we were getting the correct results. Here we can see that the yellow line is the actual temperature of the thermocouples that they're reading back to us. And then the gray line beneath that, it's mimicking the pattern, showing that we just have an offset of our thermocouple, but it's confirming that it is accurately giving us temperature. Again, this test was done without phase change material. That's why at the bottom, you will see the temperatures exceed the 50 degrees centigrade temperature. However, as we proved earlier, we can utilize phase change material in future experiments to show that we actually have a working unit. Now, Moldovan will touch upon the experiments we did when he came back to the States in the next semester.
Thank you very, very much. So when we had to make some adjustments to transition into a new lab. While making these adjustments, we encountered some obstacles when we realized that some of the temperature recording instruments were inaccurate. This made it difficult to perform controlled experiments and collect valuable. Another issue we ran into is that we didn't have while we had a thermal barrier, we lacked a phase change material, which made it difficult to perform lengthy experiments for fear of damaging our prototype with extreme. Finally, moving the prototype to the United States caused wires to get bumped loose, resulting in errors when testing our equipment. While all these problems did come up, they were eventually able to be overcome as our attack. Next slide, please. Once we solved these problems, we were able to successfully redo the proof of concept test, similar to the one Michael Kishlar mentioned. But we were able to do this one using the equipment on US. This one was performed without phase change material to match the experiment performed in France. Again, this shows that with a few adjustments, our team was able to pick up where we left off when we returned to the States. Next slide. When running all these tests, it was common that we'd run into obstacles after dedicating lots of time. You can see the format in which both our first two prototypes would display data to the console. While this is readable in the console, this format made it impossible to move data from one place to another. Prior to the semester, every test that was performed required someone from the team to manually input temperature data from each respective thermocouple. This slowed down testing and limited the number of tests we had time. Because of this, we needed to make testing as streamlined as possible with an emphasis on clean data acquisition. Next slide. This led to the creation of PyParse. This is an unparsing program that cut down on data acquisition time by collecting data and organizing it into an Excel doc. To hold to our open source claim, this was programmed in Python and uses only one non-native library. You can see down here an example of our program running, which is contained in its own self-contained folder that has instructions for use with example files for new users. Users can also name their Excel file, which will be out following data. Slide. Here you can see the data before formatting and after formatting in the Excel file. In the Excel file, it neatly shows the names of the thermocouples as well as their respective timestamps and data. Now I will move back to Michael Kishlar with the budget.
Thank you, Moldovan. So here for our budget, we have a sensitivity diagram. This shows us the percent cost for each equipment category, going from the most expensive to least expensive. As you can see, a high portion of our budget is just going to the thermal equipment itself. For this, we decided to use K-type thermocouples instead of T-type thermocouples. We discussed with our clients and we came to the agreement that the cost effectiveness of the K-type thermocouples as well as their accuracy being still within the range, although not as accurate as T-types, allowed us to purchase these in order to keep the cost down for our project as a whole. We also utilized Arduinos instead of something for, say, a Raspberry Pi, because we wouldn't need that type of computing power, but we just wanted to focus on keeping the price down with the minimum specifications necessary. In the next slide, we can see the actual price that went to each of these categories, and then a line in the background showing us how it contributed to the percent total. A huge emphasis on our project is just cost efficiency. So even though our thermocouple equipment was the most expensive, it only was $150. Everything else is still, it's under $100 for the pricing. And then if you go to the next slide, where we can actually show you the price that we are offering, like to create these prototypes individually. The first prototype, as Tony mentioned earlier, it was a bigger one. It used the Arduino Mega instead of the Arduino Micro we're seeing in our newer prototypes. And because of this, we're seeing some changes between the prototypes. For instance, for the second one, we had to utilize SD cards for the storage since the Micro no longer had enough onboard storage like the Mega did, as well as utilizing things such as a perf board instead of a breadboard to allow for us to still use the same circuitry, however, in a smaller space span than with a normal breadboard, as well as using barrel jack connectors just for the ease of our user. The total of our budget for both semesters was only $541. The rest of the price difference between these prototypes went into contributing to the third prototype that Tony will get into now.
So for the third prototype, which is currently in the design and development phase instead of the creation and prototyping stage, due to the interruption of COVID-19. So what we did to design this was implement the good features from prototype 2 and prototype 1 that we liked, and change the features towards our objectives and our goals that prototypes 1 and 2 did not meet. And so what we wanted to do was have a thinner but wider enclosure to more be like the competitors in the industry, and have a 6 to 8 thermocouple design, which you can see, which we have now, which does increase the price a little bit, as well as including an integrated PCB, a printed circuit board, which will help minimize wiring and create a thinner layout, as well as a more of a horizontal layout rather than a vertical layout in prototype 2. As you can see on the left, the CAD drawing shows the spatial relations pretty exactly to what they will be in the actual prototype. This is our widest prototype at 19 centimeters, but the height is only 3 centimeters. It is roughly $230, so it's the most expensive prototype, but it is the one. It is in the line of family of having the most features. And so with this is the end of our project, and we have some of the objectives that we've completed through these 3 prototypes and through this design phase. And so we did develop a sensor array in all 3 prototypes. They checked that off. Thermal testing with the thermal barrier, with the thermal capacity of the components themselves and thermal couples. We did that throughout the whole both semesters. We reduced the array footprint. In prototype 2, we made it smaller, height-wise and 2-dimensional footprint. But then in prototype 3, we really decreased the height to make it a lot thinner, which is really nice, even though it came with the cost of being wire. And so then the PC interface is an important part, and that was in development during prototype 3. Is being developed and is still in its working phase, and that should be completed. So from conclusions of this project was that starting from scratch allowed us to prioritize functionality. And so when we started our own code, and when Alex started coding, he completely started his own and was able to implement features incrementally, and so that he knew that everything would work. And we applied that to our physical prototyping, with using the Arduino Mega and with the breadboard, and then we implemented the Arduino Micro with an SD card after that, after we knew that the Arduino C programming worked. And so through these 3 prototypes, we've created a family of self-enclosed prototypes, and the first in the project history to have 1 self-enclosed prototype, let alone 2 and a 3rd one in the design phase. And so with these actual prototypes, we got some real life experience with connections and with moving through different circuitries. And so soldering connections for robustness in every aspect was really important. And one thing that we used a lot in going from breadboard to perf board to now PCB uses a lot more solder, and as well as creating the barrel jack connections for proper I/O ports for the user for this thermocouples. And then in open source for versatility, so using the Arduino suite really helped. Arduino and Python really helped with that, and to keep it open and flexible and changeable. And there's a lot of help out there for people who want to use this. And then PCB for an efficient layout, keeping it the height minimized, yet organization maximized. And so some things we've learned from this project is that problems arise from the simplest tests and tasks. When we first got to France, we had some trouble with our first test, so we had to do some research and keep chugging through those problems. And so it is important to keep working through problems, because if you just stall out as soon as you hit one, we would have never, gotten as far as we did. And then, if you hit a problem, sometimes design deadlines can't always be met, and it's really hard to meet those sometimes, but you have to push to make them. And then sometimes you just got to start from scratch. You got to start over, or you initially start from scratch. And that is, can help you in success since you're learning it all the way through. And then producing prototypes, getting in the lab and building, and actually getting out there and getting your hands dirty and having things fail or having things work really helps you in the whole design process. So thank you for our presentation. I hope you enjoyed it. So how was that?
Nice.
Just barely under 12 minutes, or sorry, 30 minutes.
Yeah.